In the name of Allah, the most gracious, the most merciful. Hello everyone, welcome to my presentation. Today I want to talk about multi-objective variation oversizing in analog CNFET circuits. I want to thank ICD Conference for allowing me to present my work. I am Hishmatpur and I am a Master of Engineering student at Memorial University of Newfoundland. The content of my presentation include: first, why we choose CNFET. Then we will give an introduction on carbon nanotube. We'll discuss design centering using GBC, multi-objective optimization, normal boundary intersection, and at the end we will show the circuit that we test our optimization method on and compare the results with other optimization methods. Why we choose CNFET? As CMOS dimension reduced to less than 22 nanometer, its performance encountered multiple challenges such as decreased gate control over current, increased leakage current, considerable power consumption, and tunneling of electrons. So we need a substitution for the next generation circuits. And the advantage of CNFET, such as better scalability, better control over channel formation, also better control over the current flow, high electron mobility, high current density, and the fact that it can work with lower supply voltage will enable us to consider it as a substitution for next generation circuit. CNTs are made of graphene sheets rolled up to make a cylinder with a diameter of a few nanometers. The resulting cylinder is called a single-wall carbon nanotube. If more than one graphene sheet is rolled around the same axis, it will form a multi-wall CNT. The angle of rolling the graphene sheet determines the chirality vector, and the chirality vector will determine whether the CNT is semiconductor or metallic. Here you can see a picture of CNFETs and all the parameters inside it. One of the most important parameter is the diameter of CNT, which is shown as dCNT on the right side. As you can see, it can affect other parameters of the CNFET. And the variation of the diameter of the CNT is so important because a small variation in it can affect the CNFET performance. So we consider this parameter as the parameter that we will continue to focus and consider its variation and try to optimize it. Here we can see our proposed sizing engine. We use normal boundary intersection in combination with our modified GBC method to produce our variation over multi-objective fully deterministic sizing. Our engine will receive CNT process variation, CNT circuit specification, design objectives, and at the end it will give us the optimal size for a robust analog CNFET design. A major difficulty that designers face is to develop systems or models that perform reliably in the event of process variation. Design centering addresses this issue by finding a design that meets specified requirements with high chance of doing so even if the parameter change randomly. Design optimization tries to identify the design that best satisfies the specification. However, design centering seeks to find the design that robustly meets the specification. So we use design centering to achieve a robust circuit design and the best yield functionality while having a safety margin in our parameter distribution. As I mentioned before, the diameter of CNT has a high effect on the performance of CNFET. So it's important to choose a good value for it to have a robust circuit. In our paper, the GBC method presented in reference 1 is modified to solve the sizing optimization problem without having any initial estimation of the step size change. As you can see on the right side, the gray shaded area contains the best value for our GBC. So it's important to have a good estimation that will give us the good performance. In the reference 1, they consider a random maximum x and a random m value, and they got the estimation of x based on dividing these two parameters. However, we cannot consider this in our case, because the variation of the diameter is very important and its variation is so small that we need to have a good estimation. So we consider the Bézier curve to achieve a good estimation. The Bézier curves are often used in different engineering fields to estimate soft curves. And we use this Bézier curve for estimating the GBC curve. Here we plotted the Bézier curves by using 2 initial point, 3 initial point, 4 and 5 points. And based on our observation, the Bézier curve with 5 nodes is a good estimation of the GBC curve. And we use this curve and its mathematical equations to get a good estimation of initial x that will have the GBC final value inside the gray shaded area in the previous slide. Here we can see our process of getting initial estimation. First, we define the Bézier curve and estimate the GBC curve using the Bézier curve equation. Then we will have a point that has the same x and y value. This point is located inside the gray shaded area on the right side picture. Then we will calculate the parameters for this point, and we know that the slope of the GBC curve and the Bézier curve at this point are equal to each other. So by having this equality, we can get a good estimation of x and use it in our next step. So to sum up, we use this modified GBC method to get the single objective optimization and pass this value to our multi-objective optimization to form the convex hull of individual minima, or CHIM. In some situation, we want to optimize different objectives of the circuit at the same time. So we use multi-objective optimization methods. The mathematical formulation of multi-objective optimization is shown here, where fx is a vector with n objective functions and x is a vector with n optimization parameters. Consider a case where two objectives vary in different directions. For example, the gain and bandwidth of a circuit. For this case, we cannot have one single value as x that optimize both of them at the same time. So we need to define a new concept that gives us a multiple value that will each optimize these objectives one step at a time. First, we define domination. A point is dominated by another point if it has higher f1 value and also has higher f2 value in compared with the other point. For example, consider in this picture the point C. It is dominated by 2 points D and E, because as we can see, the point C has higher f1 and f2 value than these 2 points. Also, point C will dominate point B, because point B has higher F1 and F2 value than point C. As another example, we can consider point E. No other point in this picture will dominate it, because no other point has lower F1 and F2 value than it. But point E will dominate point B and C and other points that have higher F1 and F2 value. No single X would generally minimize every objective at the same time. A concept of optimality is defined as Pareto optimality, and it is the set of non-dominated points that form Pareto front. On the picture on the left, we can see the visible region for two objectives shown by dot points, and the point F sharp is dominated by the points located on the arc between F1 star and F2 star. The visible region between F1 star and F2 star is called the Pareto optimal front, where all the points on this blue arc are non-dominated, and they are considered as the best optimum values. In order to solve the multi-objective optimization, we use normal boundary intersection method, which is a deterministic method, and its formulation is shown on the right side as equation 1. And on the left side you can see its process. The aim here is to maximize T, which is the distance from the Pareto front points, and the points are the CHIM. The CHIM line is the line connecting the individual minima of F1 and F2 together. First, we generate multiple beta, and based on that, we divide our equation 1 to multiple sub-problems. Since the specific minima of the function are already available from the first optimization phase that we use our modified GBC method, then we have the x1, and we can use it to solve a nearby sub-problem, then another one and another one. Then by solving the equation for different beta, the Pareto front can be achieved, and it is shown as the blue arc on the left side picture. In order to compare our optimization result with other multi-objective optimization, we use two metrics. One is hypervolume, which is defined as the space between a reference point and the points on the Pareto front. An example of it is shown on the right side picture. The higher hypervolume determines a better result. Another metric that we use is a spacing metric, and it will define how well our points are spaced with each other on the Pareto front arc. If all the space between the Pareto points are equal, the spacing metric will be 0. So we can conclude that a lower spacing metric shows a better final result. Here we consider a two-stage op-amp circuit and applied our optimization method to it to see its performance. On the middle picture, you can see the Pareto front generated by using our modified GBC plus MBI method and NASCA2 method. As you can see, the spacing between our method is almost similar, and we applied our two metrics to these Pareto front points, and we can see on the right side that our method reached a higher hypervolume value and a lower spacing metric value, which indicate that our method is superior than NASCA2 method for multi-objective optimization. Thank you for your attention and for your time. Please contact us if you have any question regarding this presentation.